Hey guys, I wanted to talk to you about section 1.2. In section 1.2, we're going to be talking about sampling. Now, I'm at the Wiley Plus site. Now, if we were doing an intense study of sampling, we'd be spending a lot more time on it. But what we want is to get some of the basic ideas of sampling so that we can bring that to bear on the problems that we're going to come upon later on. So I'm going to go into the 1.2 class lesson that you'll be seeing. So there'll be the notes and there'll be the video lesson. I've already opened the notes here, but I guess I wanted to show you one thing. When you click on the notes, which is what I'm going to walk you through, it opens in a little frame, which is not very useful to work with. So you're going to want to download that, and you'll probably have to either find it in your downloads folder, or if you're using Chrome, it may download here where you can click on it and open it up. All right, so let's go from here. I hit W again to make that wider. Now I want to go back here and just sort of show you the rest of that screen first. So there are going to be some links here that we'll look at as we go through this. Okay, so sampling 1.2 or section 1.2, sampling from a population. I'm going to hit F to go full screen. So sampling from a population. So here's kind of a way to think about what we're trying to do. We're thinking about making generalization from a sample to a population of interest. So we'll talk about different possible populations, but anything we want to study in statistics, we're often trying to go from some small sample to a population. So here the problem is to make inference about whether the soup is hot enough, too hot, but we're taking a small sample. So what's the implication here? Yes, sample image as well. So what's the implication? It's that in order for this to be a reasonable or representative sample, we would assume that this soup has to be pretty well mixed. Otherwise, it may be possible that it's cold at the top and warm at the bottom. So when we think about randomness or sampling randomly, we want to think about the population being sort of well mixed and that we're at least reaching in and getting some representative sample. So let's talk a little bit more about terminology here. The population includes all individuals or objects of interest. So let me try to diagram this a little bit for you. All right, so sorry, a little technical difficulties, but here we can think of as our population. And down below, some subset, which is our sample. And we're taking a selection from this population, right? So the population is the individuals or objects of interest. If we're interested in developing a treatment for people with a particular disease, then our population would be all people with the disease. We select a sample to study, and this is the set of cases for which we have data. In other cases, we might be doing, say, a public health experiment. One of the famous ones is called the N-Haynes study, and that's something that comes up in the reading or one of the problems, I believe. It's a long-term, very large-scale longitudinal study where they follow a random sample of individuals to find out lots of information about their health and behaviors over time. So in a case like that, the population would be all U.S. residents. You're trying to get a representative sample of the U.S. population. So the population that you want to make inference about here is all U.S. Adults or U.S. residents. The sample is the group that you select, but specifically it's a group for which you have data. So we would really think of it, if we were doing a survey, it may be that everyone's not going to participate in the survey. So typically we'd be thinking about the sample as the ones who actually did participate, for whom we have data. If it's an experiment, again, we may have selected from a population to study a particular disease or treatment of a condition. or a population and ecology, and then the sample is going to be those for which we have data. All right, it may seem pretty clear, but there are situations where we have to be careful to distinguish what the population is that we're actually working with. The statistical inference is the process of going from the sample back to the population. So that's the idea of statistical inference. All right, so going from the sample back to the population. So by understanding the relationship between the population and sample kind of mathematically, that gives us some information of what we can say, how we can generalize from the sample to the population. Okay, so let's continue. Going to move on to the next page. So we might consider a survey. Let's say that we're interested in finding out among case students the proportion who are interested in going on to graduate school. So we take a survey of this class, and here's some results from the last go-around with biostats. I just asked, do you want to go to graduate school or not? And you can go ahead and respond, and I'll have some responses from our class that I can tell you what we came up with. But last year, out of 25, 84% were interested in going on to some form of graduate school. 12% saying maybe. There was one who did not intend to go on to graduate school. So we could try to make inference from the sample to the population, but the question might be then what's the relevant population? So the sample would be those who participated in the study and gave results or gave information, gave responses. So suppose K is interested in the proportion of its students who want to go on to graduate school. Population would be all K students or perhaps seniors. Perhaps the population is this class. It might or might not be representative of the sample. And so we have to think about that when we think about the sampling method, whether our sample data can be generalized to make inferences about the population. And so if we thought that people taking biostatistics tended to be different from the general population in terms of their interest in graduate school, then we would probably not want to generalize from these results, the 84% to the entire population of all K students. And it probably would not be representative for lots of reasons you might be able to think about. So the concern that we have then is the issue of sampling bias. And sampling bias occurs when the method, and we want to emphasize here, when the method of selecting a sample causes the sample to systematically differ. So it's not just that the sample is wrong or problematic the way it turned out, but that the method itself had some flaw in it or some reason why it would be biased. So the idea of taking a sample from a biostatistics class to represent the entire population of students seems problematic, right? That there's something, this is, if we go all the way back to the diagram with the soup, we can think that this group of people taking biostatistics or students is not necessarily going to be representative of the whole population. It's not kind of well mixed with a uniform group. All right, so if sampling bias exists, we can't trust the generalizations from the sample to the population. Okay, so next, it looks like I'm going to have to, sorry, I'm still working on some of the issues here and working with this interface. All right, so let's move on then. The scope of interest then is what we want to think about. We want to think about how far we can generalize from a sample to a population. So the inference can only extend to a population that looks like, in some sense, the sample. So for example, one particular study was a study of treatments of anorexia in the UK. Girls who were diagnosed with anorexia participated in the study, and then they, these were ones that were willing to participate, and they tested 3 different treatments for anorexia. Because this was a sample just of those who are willing to participate, we can only generalize so far as perhaps the UK population or those who would be interested in participating. If we're trying to track a disease, incidence of a disease, if we only have data on those who visit doctors, we don't really know what the incidence would be if there are some people who consistently would not visit a doctor. So we might have this method of collecting data just based on those who visit doctors would have some sampling bias. If we want to generalize from experiments in the ARB, the Lillian Anderson Arboretum, we can generalize probably as far as the plants that are represented, the populations of plants that are represented at the ARB. There may be regional differences or differences specific to the topology or terrain environment of the ARB, and that might limit our ability to generalize beyond the particular sample that we have. So we want to keep in mind that we can only generalize as far as the population that we're sampling from. Maybe to make this a little bit clearer, we can think of ways that we could go about sampling. And so in the next part, I'm going to talk about simple random sampling and different methods. But I'm going to stop here and continue on the next part.